Suppose the bacteria population starts with 500 bacteria and triples every hour. Suppose that it starts with 500 and triples every hour. So the population, what is the population after 3 hours, after 4 hours, after T hours? So time and then population, you can make a table to help you with this. At time 0, what's the population? 500. After 1 hour, it's 1500. After 2 hours, it's 4500. 45. After 3, what is it? No, it's 130. It's 13,000, right? I'd put too many zeros there. And then what's it after 4?
47.
What?
40. Oh, wait, no. 40,000. Okay.
Okay, multiply times 3. What is it?
It's 41,000.
41,000 what?
I think it's just
41,000? Great. Okay, so then we want to figure out after T hours. So what's happening every iteration? It's multiplying by?
No, it's not. It can't be. It's just really dumb of me.
Okay, so can someone tell me what it is?
3150.
Wow, no one did this question.
3150. Or 41.
3 times 10 is 30. 9.
It is 41. It is.
40500.
Thank you. There you go. So what happens each of these iterations? It multiplies by 3. So this is going to be 3 to some power. And what's the initial population at time equals 0? Yeah, so it's going to be 500 times 3 to the t. Yeah, 500 times 3 to the t.
The question I had about that though is
Okay.
I looked, like I was trying to figure out how to do this, and looking back in the book they have an example of this problem, and they do that, but then they randomly add in the ln of 2 in there for no apparent reason.
Okay, I don't know that example. Let's just finish this one and see if we can finish it.
It's the exact same.
Okay, I don't know that example, so I can't reference the minutia of a problem I haven't seen yet. So I'll go back in a second. Let's just finish this, okay? Are we okay with that equation right there? Are you comfortable with that? That's the population after T hours, because what's 3 to the 0 power? 1. Use section 5 and 3.1 to estimate the rate of increase of the bacteria population after 6 hours. So what are they asking you to find for part B? Find the what of the what? Find the... Nope. Well, why? Because you're trying to find the... Which is the...
Slope.
Thank you. The slope of the tangent line at what? At what? At 6 ponies? At 6 hours, yes. Of the tangent line at 6 hours, so at t equals 6. So what do you need to find first? The derivative, exactly. So can someone tell me, so if this is the population in terms of t is 500, 3 to the t, can someone tell me what does that 500 do in terms of the derivative? It just, yeah, sticks around. What's the derivative of 3 to the t? Yep, it's ln 3 times 3 to the t. In class, we talked about this. We proved it. We proved it that d dx of a to the x is equal to ln a times a to the x.
We proved this?
Yes, we did that in class. It's in video and in the notes.
Okay.
We did that out. It's another definition for ln, remember? Because what is e? E, what's the derivative of e to the x? You all know this is e to the x. Why? Because what is ln e? 1. We talked about this. It's in video and notes. You can go back and look at it. So the derivative of 3 to the t is ln 3 times 3 to the t. I probably just answered your question of where did the ln 2 comes from. Okay, excellent. So what did they ask you for, though? They didn't ask you. They asked you for the derivative, but evaluated at what? 6. So you want p prime of 6, which is going to be 500 ln 3 to the... It's going to be pretty big. If it's tripling every hour by hour 6, is it going to be pretty big?
Yes.
Yeah. So do you expect the rate of change to be pretty big positive number? ln 3 is about what? It's a little bit bigger than 1. It's a little bit bigger than 1. So this thing is approximately, it's greater, well, you can just say this is greater than 500 times 3 to the 6th. 500 times 3 to the 6th is 27 squared. 27 squared is what? 684? No, what is 6? No, it's not 684. What? What is 27 squared? 729?
Yep.
And 729 times 500 is? 300,000 something?
364,500.
Yeah. So is this thing pretty big?
Yeah.
Yeah, it is pretty big. Pi times r squared. If you differentiate this with respect to t, you're differentiating this with respect to t. Yes, we didn't specifically do this yesterday, but there are a few examples, and it's not there's no super terrible algebra involved. It's going to be dA, the rate of change of the area with respect to time is, what does the pi do to the derivative? Again, it's a constant, so it just
Stays there.
stays there. What do you do with the 2? 2 times r times what?
dr dt.
Yeah, dr dt, the rate of change of r with respect to t. Do we have dr dt?
Nine.
Yeah, what is it?
60.
60. We have dr dt. You bring it down and plug it in. Right there. So what do we end up with? dA dt, sorry, dA dt in terms of r, so it's in terms of r, is 2 pi r times, well, actually not 2, we can make it, what, 120? 120 pi times r. This is the rate of change of the area with respect to time at each r value, So we have it at 1 second, 3 seconds, and 5 seconds. Huh. We have this in terms of r. What do we really want? T. We want it in terms of t. So what do? 3. You end up with what? 100. It's 3 times that, right? So 21,600 pi. And what's dA dt at? Time equals 5. 36,000 pi, like that. So it says, what can you conclude? What can you conclude? This is the rate of change of the area. The rate of change of the area is doing what?
Keeps growing.
It's going at a linear rate.
Is increasing. Why does that make logical sense? Why would the rate of change of the area, so the radius is increasing at a constant amount, but the rate of change of the area is getting fast, it's increasing faster. Why? If I have a circle that's 1 inch in diameter and I make it 2 inches in diameter, the area goes from
Radius squared is proportional.
Exactly. So if I have a circle that's 1 billion miles in diameter and I make it 1 inch bigger, how much area did I just add? A whole lot. But if I have a circle that's 1 inch in diameter and I make it 1 inch, increase the radius by 1, you've a little bit compared to the billions of square miles you've just added, or not quite a billion, but a lot. Okay. Any last ones you want?
Distribute.
You have to distribute. Yes. You know, volume is equal to 5,000 times. You could do this instead. You could break it in, turn it into this. 2 functions, right?
Yeah.
And now what can you use?
Product rule?
You can use the product rule. So v prime, so this is dv dt, is going to be what? 5,000 times, what's the derivative of the first function? This is the first function right there. What's the derivative of that?
Oh.
We're using the product rule now. Close. Negative 1 over 40. The derivative of the first times the second plus the first times the derivative of the second. What's the derivative of the second?
Negative 1 over 40.
Negative 1 over 40. What can we factor out of that, of the middle?
Negative 1 over 40.
So you end up with negative 5,000 over 40 times 1 minus t over 40 plus what? 1 minus t over 40. So if you simplify this, you end up with what? What's 500 over 4? 250 over 2? Negative 125 times 2 minus t over what? 2 over 20. Yeah. So dv dt is negative 125 times 2 minus t over 20. Yeah, exactly. At 5 minutes, 10 minutes, so can we just plug in these numbers now?
Yep.
Yeah, this is a lot nicer since we don't have to do the limit 4 times. Are we okay now? Could you finish the rest of this?
Yeah.
So we don't have the chain rule, so you have to use the product rule. How could we avoid using the product rule? We use the product rule right here. If we wanted to avoid using the product rule, what could we do? Fully distribute it out, and then we just need to use the begins with a P.
Product.
No, if we want to
Power
avoid
rule.
power rule, exactly
That one.
right. That one, yeah, that one. Okay, excellent. Sine x means the sine of the angle whose radian measure is x. So in this class, unless very specifically and clearly specified, you will always be using radians. Unless the question specifically says always, always, always use radians. Again, we use the limit definition of derivative, and we get this thing right here. Doesn't look like we can do much with this, but do you remember in Trig you had sum of angle formulas? Sine of a plus b is sine a cosine b plus cosine a sine b. If you make that substitution, we're making the substitution right here, and then break it apart into two sums, you end up with this. Oh, sine h over h, have we seen something like that before?
Yeah.
We didn't prove it, but what is the limit as h goes to 0 of sine h over h? 1. So that kind of goes away. That's kind of nice, right?
Yeah.
You can just kind of distribute in the limits functionally. Those go away. So you end up with this. You end up with this thing. We know that the limit of sine as h goes to 0 of h over h, sine h over h is 1. We'll prove that later. But you end up with this right here. You end up with this thing. You see that random multiplication there? What is this right here that I'm circling? That's just a random form of 1. So are we allowed to multiply by 1?
Yeah.
Yeah, sure. So we multiply by 1. You keep on doing some more algebra, and that's a multiplication symbol, a little box. It just didn't print nicely. If you do this all out, you end up with something that you can plug in h being 0. And you end up with 0. What we're looking at right there is not the entire thing. We're looking at, we just proved that the limit as h goes to 0 of cosine h minus 1 over h is 0. That's this part right here. You see that? So if that's 0, what does this whole thing become? 0. And what do we know this equals?
1.
What's the only thing that's left?
Cosine.
Cosine x. So we actually just proved that the derivative of sine is cosine. You can look through this. You definitely have the capability of understanding this. But in order to prove that the derivative of sine is cosine, you need the summation of angles for sine, and you need a random multiplication. Is that something I want you to be able to pull out of thin air? No. Do I want you to understand like the basic idea? So are you relatively confident that the derivative of sine is cosine? Yeah. If you do similar work, you can prove that the derivative of cosine is not sine. It's negative sine. If you do similar work, one extra little negative sign gets generated, and you end up with the derivative of sine is cosine. The derivative of cosine is negative sine. All other trig functions are written in terms of sine and cosine. So are you now able to differentiate any trig function?
Yes.
Yes. What about this one right here? Could you differentiate? Let's make this go away. Could you differentiate this?
Yes.
What rule would you be using? What differentiation?
Rule.
Use the product rule. Exactly. This would just be the derivative of the first times plus 2x cubed plus x times cosine x. Done. That's all you need to know. That's it. If I replace that cosine with sine, the only thing it would change is the derivative of cosine is negative sine. That's it. It's totally it.
And the derivative of negative sine is negative cosine.
Negative cosine, exactly. Yeah, so if you go back and forth, it'll do something
Going
fun.
in a circle.
We also now know that the derivative of cosine is negative sine. So are these really, really important things?
Yeah.
Very, very important things. Now, are you going to have to summarize all trig functions down to sine and cosine before you differentiate?
No.
No, you're going to remember shorter derivatives. But with this information, can we derive the derivative of tangent, for example?
Yes.
Yes. What about tangent? Well, tangent is what?
Sine over cosine.
So tangent x, the derivative of this in terms of x, is the same as the derivative of over cosine x. What rule are we going to use? Quotient rule. So that's going to be low d high minus high d low all over. Well, what's cosine squared plus sine squared? 1. 1 over cosine squared. What is 1 over cosine squared? Well, that's 1 over cosine x times 1 over cosine x. What is 1 over cosine? secant. So this is just secant squared x. So you just prove that the derivative of tangent x is secant squared x. That is another one that you'll have to know immediately, like instantaneous recall. Derivative sine is cosine, derivative cosine is negative sine, derivative tangent is secant squared. You need to know these cold. What is your most valuable asset on the AP exam? Time. Knowing these things saves you time, and this is like knowing vowels in speaking English. This is speaking calculus. You have to know these things. You have to know these things. Squared, you end up with 1 plus tangent squared x equals 1 over cosine is secant squared x. So that's dividing by cosine squared x. What happens if we divide by sine squared x? You end up with cotangent squared x plus 1 is equal to cosecant squared x. So if you just remember this, can you easily divide the other two?
Yeah.
I always forget the other two. So what do? It takes me literally 3 seconds. Remember where they come from. Very, very, very important. Never forget those. This one right here. Secant over 1 plus tangent x. If we do that out, what's f prime going to be? What rule are we using? Yeah, what's the derivative of low? What's the derivative of the top, Bissell? Bissell?
Secant x tan x.
Yeah, the derivative of secant is secant x tan x. You see how derivatives of trig functions tend to explode? Low d high minus high. What's the derivative of tangent? Or 1 plus tangent? Secant squared x all over
1 plus tangent
1 plus tangent x quantity
squared.
squared. Exactly. Now, could you multiply this out, maybe simplify it a little bit?
Maybe.
Maybe. Please don't obsess over trying to find some absolute awesome simplification because of 2 reasons. 1, 3, you might not need to. It might not be necessary. Like if you just need to evaluate that, evaluate it right there. 2, it might not have a clean substitution. Or 3, it might be just a complete waste of time for some other reason. So unless you really need to, if I ask you, that's the derivative. But for example, what's one thing you could clean up really easily right there?
You could cancel 1 plus. No. You
No.
couldn't.
Cube, secant cube. Sorry, I had to stop that before you said the whole sentence.
Yeah.
That secant cube, like you have to do little things like that. The other thing that drives me crazy too is I give this question, you guys have too much time, and then you start simplifying it different ways. Are there a million different ways to write the same trig function?
Yeah.
Yeah. So you could all be right and have a different thing written down, and my head just goes, "Rah." Brain melts. Even on like relatively simple differentiations, could you write it very differently?
Yeah.
Yeah. Also, 4th reason, by simplifying, you could make a careless mistake. You could be like, I'm going to cancel those. No.
Your
no.
head was in the way of the secant.
Oh,
in
my
defense.
head was as big as the secant? Okay.